So welcome to this class. Now the last classes we discussed about the atom probe tomography, we discussed about the sample preparation, focused ion beam, use of focused beam for sample preparation, and we also talked about the reconstructions and the use of how to use the atom probe to get the chemical information. So if you go back to my the first class, I introduced you this course as a advanced microstructural characterization by atom probe tomography and electron microscopy. So from now on onwards, all the lectures will be focused on electron microscopy. Okay. So in the electron microscopy, what we will do is we will cover basics related to the TEM, and one more advanced technique which we uses now is SEM based, which is related to ECCI, which is electron channeling contrast imaging. Okay, and also we will basically cover based on SEM based techniques. Briefly we will cover to the EBSD and TKD. Okay, and why these techniques we need to introduce is these techniques will be used in correlation to your TEM, and I will show you that how these techniques can be used together with the atom probe tomography, where from here you will get most of the structural information from macro to atomic scale. Then how these information, the structural information, is correlated to your atom probe tomography, where you will get the chemical information. Okay, and these all techniques, electron microscopy can be used to visualize or see the grain boundaries, grains, phases, precipitates, defects. Okay, and in the introduction also I mentioned that these are controlled by the phase diagrams, solidification and phase transformation, that overall controls the property of the any microstructure or alloy. Okay, so this is the composition, this is the structure, and we have basically covered the reconstruction. So I will show you in the last classes, few classes, maybe 2 or 3, that how this atom probe tomography can be used with electron microscopy to get the correlative information of structure and chemistry. Okay, now we will focus on the mostly on the electron microscope or the transmission electron microscope. Fine. So the content will be in the next 10-hour lectures or next around 18 to 20 lectures. What will be the content is the basics. I will cover the basics of image formation, resolution, aberrations. Okay, these are very important to understand the image formation in the transmission electron microscope. Then we will briefly go through the electron interaction with the sample surface, where and what are the signals which we get in the microscope, in a typical microscope, be at a transmission mode and be at a scanning mode. Then we will little bit talk about the electron diffraction, the principles behind the electron diffraction, and what are the reciprocal space. So these things will be covered, and the basic construction of TEM, and how this electron diffraction is used for imaging the sample features. Fine. And if time permits, we will also go through briefly about the chemical analysis in electron microscopes. Okay, anyhow we have covered in atom probe. Then there are other techniques which is I told you based on the ECCI and the TKD and the EBSD. These 3 techniques I will cover briefly. Then I will show you some of the case studies which is based on different alloy systems. So as a metallurgist, you will be, as a materials engineer, we deal with the different types of alloys, either be the steels, either will be the super alloys, either will be the aluminum alloys, either will be the semiconductors. Okay, how these all the techniques can be used to understand the microstructural behavior of these alloys, which controls the overall property of the alloy. Fine. So with this, what we do is we will introduce the basics related to the image formation. So if you have any object, fine, you use an optical system. Okay, so this is the basics related to your any optical microscope. This optical system, the main function is to magnify that particular object so that you will create an image, okay, which is at a very high magnification. Okay, and to understand this magnification, so optical system, and to magnify the object, there are several parameters or several important concepts which need to be understood, and which is very common to either you go to the optical, either you go to the electron microscope, either you go to the scanning mode or the TM. These important concepts will not change. Okay, so the basic concept is magnification, resolution, depth of field, and aberrations. Okay, so these are the four common concepts which are important for most of the optical systems or the electron systems. Fine. So briefly, if you see that in SEM, in a scanning electron microscope, where you are actually beam rasters on the sample surface. Okay, and usually they will give you the information related to your morphology, shape of the sample, of the sample features. Fine. So this is a typical electron microscope where we can do the in a scanning mode. Okay, and in this SEM, usually we can perform electron backscatter diffraction, you can perform electron channeling contrast imaging, you can get the X-ray spectroscopy, which is related to the energy dispersive spectroscopy. Okay, which gives your chemical information at the local scale. We can also use for the WDS. Okay, so we will also cover about something about some basics related to WDS, which is a wavelength dispersive spectroscopy. Okay, so the difference between the X-ray spectroscopy and wavelength dispersion spectroscopy, it is related to your resolution, energy resolution. Then, so this is your scanning electron microscope. So in a transmission mode, in an electron microscope, you usually use a very thin specimens. Okay, so and in these thin specimens are electronically transparent. Okay, so this is a typical instrument of TEM, where the beam, a high energy beam, which is accelerated from a large potential, it passes through the thin sample. Okay, and you can get the diffraction pattern, we will cover to that. We can get to the diffraction contrast to identify the phases, and also the electron beam can be used to image the atomic structure or the atomic columns in a certain crystallographic direction of that particular phase or the material or the alloy. Correct? So these atomic structures can reveal the internal defects, phase boundaries, okay, or the crystal structure. Okay, so these things can be done by the in transmission mode by using the transmission electron microscopy image. Now, if you see an image formation, there can be three types of image formation. The first one is projection. Projection is nothing but how the object is projected, or you can actually mimic to the projection of shadow. Okay, so if you have an object, if you have a source, and if this source is light source, if the light is projected on the object, at the back you can see the image formation. Okay, so this is a very basic example of projection image. So you must have seen the projectors in classrooms or during presentations. Usually they will project your screen onto the wall or onto the projector screen. Okay, so this is the basic form of an image formation. The second is optical image. Optical image, what is the difference? They use conventional lens systems. Fine. So you can see that this is a lens here. This can be an optical lens as a glass lens, or this can be a electromagnetic lens. Okay, these will come in later classes. Okay, and based on the position of the object, you can get different types of images. Okay, so this is by the conventional lens systems, optical images. Then another one is the scanning image. This also uses a conventional lens system, but here the difference is each point on the sample surface is scanned or is presented serially with high frequency beam. Okay, so if you have a sample surface and if you have a beam, this particular beam is rastered in x, y and direction. Okay, so the beam will raster at each point of the sample surface and it will give you the image by converting the whatever the interaction of the beam with the sample, those interaction signals will be converted to your image formation. So this is called scanning image. Scanning image, usually they are used in SCM and TM. Optical images, mostly these are used in optical microscopes where there is no scanning of the beam. Okay, so these are the basics of the image formation. Now, so here I am showing you a typical optical system. So here the ray diagram shows the concept of focal length, and magnification. Okay, based on the position of the object, this is your object. Okay, and here u is the distance between the lens and the object, and here this black dot is related to your focal point of that particular lens, and based on the position of the object relative to the focal point, you can actually see three types of images, three types of conditions. Okay, so in the first condition, this is your first condition where the object is placed between the f and 2f. So assume this is a 2f position. If the object is placed between these two positions, the image is magnified, real and inverted. This is your image. Okay, so there is a source of light here. That source of light, it hits to this particular object. Then you can see this ray diagram. It passes through the focal point and it will form a real image which is inverted and magnified. So you will get a magnified, real and inverted. This is when your object is placed between f and 2f. If the object is placed, as in the second case, in between the f, okay, so this is your object, this is your object. Now in this case, the image is erect if the object is placed within f, but it is virtual, it is not a real image, and it is magnified, and it is not inverted, but it is virtual. Correct? If the object is placed well away from the 2f, so this is your 2f point, well away from the 2f, then the image is demagnified. You can see that this is your object and it gets demagnified. It is real image and inverted. Okay, so the first condition and the third condition is used for magnification or for demagnification. Okay, and based on the placement of the object with respect to the focal point of the lens. Now, if here one important principle we need to understand is the principle of reciprocity. Okay, and what is this principle? It shows that the effect on the light rays does not depend on the direction in which the light is traveling. Okay, so this is the principle which will be very important to understand this. Okay, so in conclusion, it can be summarized by a basic thin lens equation. Here, what is the thin lens equation? The f is the focal point of the lens, u is the object distance, and v is the image distance. And this is your focal point. okay. And magnification is nothing but, you can put it as you can see that this particular triangle, this is one triangle and the another triangle, triangle 2. If you see the symmetry of these two triangles, the ratio or the magnification, the image or the object, the size of the image and the size of the object is directly related to the distance between the center of the lens to the image, which is V, to the distance of the object from the lens center, which is U. So magnification can be given by V by U. And by using this thin lens equation, you can actually get the magnification as F minus U minus F or V minus F by F. Okay. So if you measure the image distance and if you know the focal point of your lens, then actually you can calculate easily the magnification. So for large magnification, your V minus F must be small, U minus F must be small and positive. Okay. So for large magnification, this particular U minus F should be small and also it should be positive, then only you will get the large magnification. Okay. And this is achieved only by placing your object just away from your focal distance, focal point of the lens. Okay. So this is your simple lens system for image formation. Now we will go through little bit deeper that whatever you are getting the inverted image, in this case, this is your inverted image, you can use another lens system into the system to make this inverted image as a non-inverted image. Okay. So here I will show you some of the basic construction of these lens system. Now you have an object here which is placed above the focal point, okay, which is at f1. Assume it is a focal point of the lens, the first lens, okay, and there is a second lens which is introduced after the inverted image of the object, okay, which has a focal point f2. Fine. So this particular second lens is called projector lens, and this particular first lens is called objective lens. Okay. So here we are introducing a new term which is a projector lens. The objective lens, the function of objective lens is it will provide an inverted image at B. And the importance of projector lens is it gives your upright image of the image formed at the B. So this is your first image, this is your projected image. So this will give you the upright image of the first image which is formed from the objective lens. Okay. So the magnification at this position B will be given by the earlier formula, which is by V1 minus F1 divided by F1. Correct. Now this particular, the size of this particular image is magnified again by using the projector lens. So it will give a further magnification of V2 minus F2 divided by F2. So the total magnification is given by this particular equation, which is V1 minus F1, V2 minus F2 divided by F1 into F2. So if you know the distance of first image, the V1, and the distance of the upright image, which is V2, and if you know the focal points of the two lenses, then you can get the exact magnification of that particular original object. Sometimes they also use second projector lens also. Okay, so from the basic optical system we went to a next stage where we are introducing a projector lens. Because of the introduction of the projector lens, the first lens which is used is termed as objective lens. Objective lens is usually termed as the lens which forms the first image in any microscope. Okay, even in transmission electron microscope you can see that there is an objective lens. Okay, and whatever the image is formed, that has to be magnified and projected in upright. So that's we use as a projector lens. Okay, now in the next slide what I will show is, till now what we have assumed is your object is self illuminated. Your object is self illuminated. It means that the object itself is acts as a source. It emits light. That's why we are able to form the image formation. That's why these light rays are passing through these lenses. But it is not the case. Okay, so what is the assumption? The object is acting as a source where the rays are starting from the object and it ends at the screen where the image is, where the final image is projected. So here the illumination is very important from as a source. That's why the next thing comes as a one more attachment which is called a condenser system. Okay, it means that before the objective lens, before the object or objective lens system, you will have a certain light source. Okay, and that light source, if your object is transparent, then illumination is behind the object. If the object is opaque, illumination is from front side. Okay, so there are two arrangements here. One is, if your illumination is behind the object in this position, this is an object. If the object is transparent, then your illumination is in this direction. The rays will fall in this direction. But if your object is opaque, then usually what they use a source of light. Okay, source of light in this by using the condenser lens system, and they will use a half silvered mirror so that it will be illumination from the front of that particular opaque object. Okay, so now we are introducing here a condenser system. So as the name suggests, condenser, it condenses the light or the light beam. The main function of condenser system is to condense the source, condense the light, correct? So this is called condenser lens system. So if transparent samples, as we know that most of your biological samples are transparent, so you use the light source behind the object, and most of the metallic samples or the bulk samples, they are opaque objects. So you will use the light source in front of the objective lens. Okay, so what is the condenser system? As I told you, it is necessary, the condenser system, it is necessary to collect the light which is diverging from the source. You can see if there is a light source, is a point source, you can see that the light is diverging. Okay, and to make it this divergent light rays in a convergent way, or to converge these light rays, you use the condenser lens system. And this condenser system, two main functions. One is the object appears brighter, contrast, you will improve the contrast. The second is it is used to control the angle at which the illumination arrives at the specimen. Okay, so this is the function of the condenser lens system. And similarly, in the transmission electron microscope, you have a condenser lens system, you have an objective lens system, and you have a projector lens system. And these three systems are common to any microscope, either it is optical, either it is scanning electron, or either it is a transmission electron microscope. Okay, and this condenser lens system in TM, usually it is used to converge the beam, which is very important in TM. So convergent beam diffraction patterns to take it. So we will come to that in the later stage. But remember, the for any image formation and in basic electron microscope or the optical microscope, these three main systems are very much needed: condenser system, objective system, and the projector system. So you can see that at each lens system, either it is an objective lens system or a condenser lens system, you can see that these are called apertures. So these are called variable apertures at conjunct lens. So these apertures are very important to control the area of the specimen which is illuminated at the angular spread. Okay, so these apertures are used to control the area of the specimen. Okay, so if you see in the optical system, we talked about the magnification, and magnification is a function of the final image distance from the lens and the object distance and also the focal point. So in light microscopes, usually as in this equation, usually the variation of V1 and V2 is very difficult in optical microscopes, but F1 and F2 is feasible. That's why in light microscopes, usually you will change the lens when you want higher magnification or lower magnification, because changing the distance of the image or V2 or V1 or the U1 is very difficult in optical system, in optical image system. So you can vary the focal point F1 and F2 by changing your objective lens of different focal point. Okay, but in electron microscopes, you don't have to change this problem will not be there. So this parameter can be adjusted. Okay. So if you compare any lens system magnification, you can see that light microscope, the resolution is around 200 nanometers because it uses light as the source, and any human eye can detect up to 0.2 mm in size. Okay, so here there is comes another important. So you cannot so there is no requirement in magnifying the smallest details, which can be resolved up to 200 nanometers up to a large size of to 0.2 mm. Okay, so any magnification which is larger than 1000x makes the details larger and larger. So you can magnify infinite times. You can magnify it. The thing is, even though if you are magnifying, but the finer details which is cannot be resolved. Okay, so there comes the resolution. even though you can magnify higher and higher, but if your final detail, it is not necessary that the 2 points or the finer details can be resolved by magnifying. Okay, so then as I told you, it comes the resolution. Okay, so what is resolution? To understand the resolution, first is you need to understand the numerical aperture. So what is numerical aperture? In any lens system, in an optical lens system, if you have a lens, it has a certain numerical numerical aperture. What is numerical aperture? It is the measure of its ability to gather light and resolve finer details at a fixed object distance. At a fixed object distance. So now if you have a lens, fine. Now you have a object here. This is your object, and this is your light beam. Okay, this is your lens system, and this is fixed here, which we term it as a D. Okay, and this is your beam. The whole angle is theta and the half angle is alpha. Okay, and the distance between the lens and the object, this is your object, is small d. Okay, so the angle alpha is the half angle of the angular aperture. So this is your angular aperture theta. Okay, so this is your angular aperture theta, and this has to be converted to the numerical aperture. So usually the NA, numerical aperture, is given by n sin alpha. Here the n corresponds to the refractive index of the imaging medium. Okay, and usually it varies from 1 to 1.51. 1 is for air, 1.51 is for oils. This is your definition of a numerical aperture, and any lens system will come with this numerical aperture. Fine. So as per the formula and numerical aperture, this will be maximum when your alpha is equal to 90 degrees, because sin alpha highest value is 90 degrees, right? So means sin alpha is equals to 1. Okay, so based on this, what we can do is, if you have an objective, this angular aperture, fine. So based on the distance between the object and the lens system, you can actually see that different numerical apertures can be achieved. So for example, if you have an object here which is at the same place, now this is your, okay, so the beam, you can see that at each condition your angular aperture increases, correct? So this is your angular aperture. Okay, and this is your object. Now with this you can see that if the mu changes, or if the alpha changes from 7 degree to the 60 degrees, so this might be the 7 degrees to the 60 degrees, because it's a half angle, correct? This is your theta, sorry, these are your theta, this is your alpha. This is your alpha. Okay. So as alpha changes from 7 to 60 degrees, your numerical aperture changes from, assuming it is in air, 0.12 to 0.87. Okay. So it means that if and from this formula, if n is high, your Na also will be high. If the refractive index of the medium is high, then Na also will be high. Okay. So the importance of numerical aperture will cover in just another slide. So before going to the actual effect of the parameters on the numerical aperture, we also talked about resolution, which is actually given by the Rayleigh's criteria. Okay. So what is Rayleigh's criteria? Rayleigh's criteria is nothing but the closest spacing between 2 points which can be clearly seen through the microscope as a separate entities. That is called Rayleigh's criteria. Okay. So this is not the same. This condition or this is not the same as the smallest point which can be seen by magnifying it. Okay. So this is called your resolution limit. Okay. This is called your resolution limit. Now to understand this resolution limit, we need to go through little bit explain about the diffraction limit. Okay. So even if you have a microscopes, all the lenses will not be perfect and introduce distortions in the image. Okay. So as your light travels through the space, so there will be a bending around the obstacles, interfering constructively and destructively. Especially these light rays, if moves around pinholes for a light, then the parallel beam of light, which is a spot, transformed into a series of cones that are seen as circles known as airy rings. So if you have a pinhole and if your light passes through this particular pinhole, you will have a concentric rings in 2 dimension. And if you see in perpendicular to this screen, you will see that these are the concentric rings. These are called airy rings. And the diameter of the central ring, the particular diameter of the central spot is inversely proportional to the diameter of the aperture or the opening of the pinhole from which the diffraction is occurring. Therefore, smaller is the aperture. This is the big aperture, this is smaller aperture. Therefore, the smaller is the aperture, larger will be the central spot. Larger will be the central spot. So the diffraction can occur from every small point in the object and it can suffer the diffraction. Okay. So the small points in an object can also become airy disk in the image. This particular airy disk, the intensity will be maximum at the center, and there is a disk which comes after a particular distance, it increases, again it decreases. This is directly related to your constructive and destructive interference of the diffracted beam or the light. So for a circular aperture, if you have an aperture of circular of diameter d, the first minimum is the diffraction pattern occurs at theta equal to 1.22 lambda by d. D is the aperture size. Okay. Here lambda we can take it as a light, which is equal to the wavelength of the light, and this relationship has come up from a Bessel's function, will not go into detail about the Bessel function. So Bessel's function is nothing but the light intensity I theta is a function of I naught 2j1 ka sin theta whole square. Okay, so it means that the j1x is given by Bessel function of x. So in this Bessel's function, the first minimum occurs at this position, theta equal to 1.22 lambda by d. Now we will understand about the so it minimum means, so if you have an if you have a aperture or the pin or the pinhole, if the light passes through the pinhole, so what will happen is, if you project on the screen, then you will have a large central peak of intensity. There will be a minimum, then there will be increase, then where there will be minimum, there will be increase. Okay. Now the first minimum which is appearing, so this is your central point 0. The first minimum occurs at a distance of 1.22 lambda by d. D is the diameter of that particular aperture, which is, this first minimum is related to the theta, the first minimum appearing in the function. Okay. Now we'll introduce the Rayleigh's criteria here. Okay. Now what Rayleigh's criteria tells us that if there are two objects O2 and O1 and they are self-illuminating objects, and if it is passed through a pinhole, okay, and if you project the intensity on a projector, these two objects can be resolved only when the minimum of one object is at the maximum point of the another object intensity. It means that if the intensities of the maximum point of one object merges with the minimum intensity of the second object, and this is the minimum distance which can be resolved by the Rayleigh's criteria. Okay, so here you can see that this case, the first case is resolved, the second case is the Rayleigh limit, and you can see that in the third case these two intensities are not resolved. So this is not resolved as per the Rayleigh's criteria. Okay, so remember, the first minimum of the diffraction pattern matches with the first the maximum part of the other intensity or other object intensity, and the first minimum occurs at theta equal to 1.22 lambda by d, which is given by this formula from 0, which is derived from the Bessel's function. So two points are just resolvable if they are separated by an angle theta. This is called theta minimum, which is equals to 1.22 lambda by d. Here lambda is the wavelength, which shows that it is a function of wavelength which the light is used, and also the d. Okay, so diameter of the aperture. So the microscope resolution. The microscope resolution can be defined as the ability of the lens to produce sharp images of two closely point objects. Okay, so if you have two objects, okay, and this is your lens system. If you do it here, this is your theta, this is your x, this is your distance between the lens. So these two objects the smallest distance x by which the object can be separated is the resolution. So according to the Rayleigh, theta is equals to, from the Bessel's function, it is around 1.22 lambda by d, and from this geometry, which is equals to x by d. D is the distance between the two objects, correct? With the small angle approximation, usually we can call as a tan theta equal to sin theta, which is equals to theta. Therefore, the resolving power x is given by 1.22 lambda by d by d. This is your resolving power of any microscope. Now, just now we covered the numerical aperture, right? Just now we covered the numerical aperture. So based on the numerical aperture, the formula which is given by NA equal to n sin alpha, correct? Now by using this formula, we can connect the resolving power with the numerical aperture. Okay, so theta equal to x by d, which is by the geometry, you can also call it as a d by d for small angles. Okay, so as the sin theta is equals to d by d. Now, for any microscope, okay, so here these are the two. So this is x is the resolving power, and this is your microscope objective, and this is your theta, which is an angular aperture, and this is alpha is the half angle of that angular aperture. Now this is your object. The distance of the is d, and the small d is the distance of the object from the lens. So from this geometry, what we get a formula is x is equals to 1.22 lambda d by d. Okay, this is your theta. Fine. So now by using these two geometries, you can see that the theta is equal to x by d, which is equals to, if you compare these two geometries, it is equals to d by d. We know that then sin theta by 2, we know that theta by 2 is alpha, is equals to, if we assume that for small number approximation sin theta is equals to theta equals to d by d. So this can be written as theta by 2, which is equals to x by 2d given by d by 2d. Hence the sin alpha can be given by d by 2d. So here 2 sin alpha is equals to d by d. Now we know that the NA is given by n sin alpha. Fine, and we have x equals to 1.22 lambda by d. So we can write x as 1.22 lambda by 2 sin alpha. And with this, if we substitute the NA into this formula, then we will get the x is equals to 0.61 lambda divided by NA into n. Here NA is the numerical aperture and x is the resolving power of the microscope. Okay, so it means that larger is the NA, x will be smaller. So it means that resolving power will be higher. Okay, here lambda is the wavelength, and here the n or the mu, you can call this particular n is the refractive index. So you can see that by decreasing the lambda, your best resolution is achieved when you are decreasing the lambda and increasing the refractive index or alpha. Okay, best resolution means x should be smaller. Okay, so for your light, your lambda is, green light is around 400 nanometers, and if you do the mu in oil immersion, mu will be higher, and sin alpha should be towards 1. It means alpha should be higher. Okay, so then you will get a maximum best resolution based on the lambda, Na, and the refractive index mu. Okay, so I hope that now you have understood about the basic concept related to the resolution. Okay, and this particular concept is same for all the microscopes, even it is the optical microscope and the electron microscope. Okay, so with this I will end this class now, and we will talk about more related to the depth of field and depth of focus, and how important those terms are for imaging purpose. Okay, so we will meet into the next class. Thank you.